Okay, well, good afternoon from where I'm sitting at the moment. So, good morning or good evening, wherever you are out there in virtual world. So, at this point, we have wrapped up colligative properties and solutions, and we're moving on to the next major topic, and this is chapter 12, chemical kinetics. Now, I gave you an overview of chemical kinetics during the very first lecture, so we're going to extend that. And so I've got this chopped up into a whole bunch of videos here, and it says that we're going to be doing weeks 6 and 7. Well, we'll probably extend that into week 8, unless we are all just collectively really motivated here. So, a little bit different before we get started. What I'm going to do is show you two case studies of two different chemical reactions. One is one we've already discussed, the synthesis of ammonia, and the other one is one straight out of your book from section 12.1, the decomposition of hydrogen peroxide, H2O2. So I'm going to use some graphs and do a lot of talking and doing a lot of labeling before we take any official notes. So I think that would help to get the concepts down before we just start to formalize things with notes. Also, just so you know, chemical kinetics in the next chapter as well on chemical equilibrium involve a handful of concepts and then a lot of specific problem types that you'll want to kind of know how to do those types of problems. And I'll try to be very deliberate about letting you know what sort of algorithm to apply to those problems. Well, enough talk, let's get started. Show and tell, before we get going here. I left this on here from last year. This is kind of interesting. You all know that carbon dioxide is the most prevalent greenhouse gas that's discussed in respect to climate change. Methane, CH4, is another one. So lots of discussion going around about how do we reduce our dependence on fossil fuels, which necessarily means how do we reduce the amount of carbon dioxide that we put into the atmosphere, and then also that gets reabsorbed into the oceans and causes things like ocean acidification, makes the pH of the ocean go down, and that affects all kinds of things. Lots of things that can happen there. Simply electric cars, power plants, uh, not burning fossil fuels to heat homes and things like that. Those are the big scale things. There is one idea that we need to scrub, if you will, the atmosphere of carbon dioxide. We need to simply remove it and get it out of there and do something with it. So this is an interesting technology. This is a schematic. This is not an actual picture. This is a artist rendition. I came across this company in Australia that essentially sets up these giant fans and it pulls the CO2 out of the air, but then does something with it. Now, what you have over here on the right side is what's called CCS, carbon capture and sequestration. The idea here is that you can take carbon dioxide away from something. In this case, the example is a, a power plant of some kind. So you take the CO2 and you do some things with it. Well, one of the things you can do, I'm a little skeptical of this one, is you basically store it underground. Old coal mines in Pennsylvania have been discussed for doing this. The other thing that you can do with carbon dioxide is try to do something with it. You can, you can liquefy it, and then you can actually use it as a feedstock to do other things, like manufacture other products. So this is all kind of, it's being done on a small scale, but it's just something that is out there. So that's just show and tell for today. So let's get right to it. I have a bunch of blank slides here. I don't know if I'm going to need all of them. So what I have are two case studies, and I'm going to put all the definitions and basic concepts here to kind of let you see them before we take notes on them. So the first one is ammonia, and we've done this one before, synthesis. And you can recall that this is the chemical equation. 3 hydrogen plus 1 nitrogen, I'm not going to write the 1, producing ammonia. And that's also a gas. And this is what's called a heterogeneous equilibrium. Everything is a gas. That's important to know for down the line. So this is, or excuse me, this is a homogeneous equilibrium. Everything's a gas. If something here was a solid or a liquid, that would affect some of the math that we will do later in the semester. So kinetics, chemical kinetics is all about the speed of chemical reactions. So what we do is we monitor the amounts of chemicals over time. And perhaps you'll recall, this is many weeks ago now, that what we do is we put time, and I'm not going to bother with putting units, seconds, hours, days. It depends on how fast the reaction is. It could be years in the case of something like radioactive decay, which we will also talk about. On the y-axis, we put some measure of amount. So in terms of a gas equilibrium, we could measure concentration. That's what the brackets indicate, like molarity. Or we could actually use a proxy measurement like gas pressure, assuming we have some kind of probe that can specifically measure hydrogen, nitrogen, or ammonia. Now, this is just a thought experiment, and I'm going to try to do this as clearly as I possibly can. So ammonia, I have to stop saying that word so. I'm worried about my mannerisms. Ammonia is being produced. So at time 0, so this is an actual origin, 0, 0. At time 0, there is no ammonia. So this is the hypothetical starting point. And ammonia will go up and then reach the equilibrium region. Go back to that first lecture or set of notes if you need to remind yourself of kinetic versus equilibrium region. I don't want to relabel all that. That'll be confusing. Fine. Now, I'm going to stick with this. I'm kind of winging these notes a little bit. I've got them in front of me, but I want to try to be more clear. If we want to measure the rate of this reaction, we could use anything. We could use hydrogen, we could use nitrogen, or we could use ammonia. They're all tied together through their stoichiometric coefficients, and I'm going to get to that. So if we want to measure the rate of this reaction, there's a couple of different ways we can do it. If you measure the rate right at the beginning of the reaction, rate is a change in concentration versus time. On the graph, it's really a slope. So if I take this point and do a tangent line right here and measure the slope of that line, that would be the instantaneous rate with respect to ammonia. Fine. We could also, or that's, I'm sorry, that's not the instantaneous rate. That's called the initial rate of the reaction. That's typically where the reaction is the fastest, is right when the reaction gets started. If I wanted to measure the instantaneous rate, well, that would be, say I want to know what the rate of the reaction is at this particular time. I just kind of chose that arbitrarily. Well, that would be the tangent, if you remember math or calculus classes. That's not a very good line. In fact, I'm going to erase that because it looks like the rate's going down. So something like this. That's terrible. That would be called the instantaneous rate. Again, we could do that. That's a little bit difficult to do mathematically. We want to be able to do things in here that illustrate principles. And the principle I want to know, you'll hear me shuffling through my notes here a bit. Hopefully I'm getting this right. Is we can actually take data at 2 different times and then just take the slope, assuming it's linear. That's an assumption we make. And we call that the average rate over a given time interval. What does that mean? Say we want to know the rate of reaction between this time, so we would call that time 1, and this rate. We would call that time 2, and kind of just connect the dots. That's called, this is getting a little messy, the average rate of reaction. That's fine. So there's 3 different ways to measure rate, And we will use most of these. In fact, we're going to use mainly initial rates and average rates because it's something we can do. And in terms of symbols, well, let me kind of get skimming around through my notes here. So if we want to define this more mathematically, now those of you that have had calculus will recognize this as a differential, like a dx dt, a change in something over time. But here, what we're doing for a rate, and this is for ammonia, we are measuring the change in the concentration. Let's just stick with concentration. You could use pressure. The change in concentration of ammonia over time. And that's either gotten by the slope of the line or by doing, if you have the data from T1 and T2, you would take, let's see, how do you want to do this? We would take the concentration of ammonia at time 2 minus the concentration of ammonia at time 1. So that'll be a change in concentration over, well, T2 minus T1. Fine. And for ammonia, this is going to be a positive rate because it's being produced. So that's just kind of to get used to seeing some of the symbols, and that's fine. Now this graph is a little messy, so I'm going to try to go to another slide here. The rates of reaction with respect to hydrogen and nitrogen are going to be negative. All right, so let's go to the next slide and rewrite this graph. I'm going to try to get all of this in on one slide. Maybe this will be a little confusing. So time, concentration. I don't want to put a specific chemical there. And we have ammonia going like this. Nitrogen and hydrogen, there's a 3-to-1 ratio there. So I did this before. I put, let's see, nitrogen starting here and hydrogen about 3 times higher than that. This is just conceptual. And we have hydrogen is going to be lost really quickly, and then it'll level off. Nitrogen is not going to reduce nearly as much. It'll be 1/3 the rate, and will come like this. We can relate the rates of these chemical reactions through the chemical coefficients. How do we do that? Well, all right. Let's see if we can relate these for nitrogen. Hopefully this will make sense. So we can use the stoichiometric coefficients here. So we already defined this as our symbol for the change in concentration of ammonia over time, and that's going to be a positive value. Now we know from the stoichiometry, and we can do this, for every 2 moles of ammonia produced, we only get 1 mole of nitrogen consumed. Okay, well that's going to be, if you do that, so basically if you cut the rate of ammonia production in half, that will equal, now we have to put a negative sign here, that will be equal to the rate of loss of ammonia. Okay, well, what does that mean? So we can relate the rates. So if you take 1/2 times the rate of change of ammonia, just take that number, cut it in half, that will be equal to or if you want to, take the 2 and put it on the other side. I think this is actually harder to do with math rather than just to think about it. And, oh, this should be change in concentration. Change in concentration. Get the idea? So it's negative for the nitrogen because it's being lost. So the rate of will be twice that. The rate of loss of ammonia will be twice that. Now I'm going to leave this up to you to kind of think about a little bit. If you want to relate the ammonia to the hydrogen, see if you can figure this one out. And I'm going to write everything in terms of just a rate of ammonia. Well, that's going to be equal to negative 2/3 times the change in concentration of hydrogen over time. So that allows you, the stoichiometric coefficients allow you to relate these. Your book has some great examples here. I don't want to do too many of these. And just to give you a generic way of looking at this, how do you relate rates of reaction for any chemical equation? And it's actually pretty easy. Let me just give you the generic equation. So if you have, I think I did this for equilibrium, A moles of A plus B moles of B producing C moles of C plus D moles of D. It's pretty simple. If you want to equate all of these rates, well, negative 1 over A times the change in A over change in time is going to be equal to negative 1 over B times the change in B over change in time will be equal to positive 1 over C times the change in C over change in time, which equals to positive 1 over D, change in concentration of D over change in time. That may take a little bit of time to digest, but this allows you to relate. Now, these are not the rates. These are the rates. So if you want to equate those, you have to rearrange the A's, the B's, and the C's. It's really not that big of a deal. So that's kind of an overview of the whole thing. Is the overview of chemical kinetics. How do you relate rates to one another? And I want to show you another case study real quick, and probably not do as much of this that I just did. I'm not going to repeat all of that for the next one, just so you see another example. And I won't make as many notes here. You can listen to this as many times as you want. The decomposition of hydrogen peroxide. The place you may see this is if you have a bottle of hydrogen peroxide, if you use it for cuts or use it to color something like your hair, and you look at the bottle, it has an expiration date on it, or you just figure out that it's not working very much anymore, or there's a bunch of bubbles in it, it's decomposing. Well, here's the chemical reaction. This is a heterogeneous reaction. So you have hydrogen peroxide, which is an aqueous solution, typically. It decomposes into two very simple things, water and oxygen gas. And I think we have to put a 2 here. So if you want to, stop the video. See if you can make the graph. What would these three chemicals look like? And let's just use concentration and time, just generic. What would it look like? How would you draw the graph of hydrogen peroxide, which is being lost, water, and oxygen being produced? Okay, and just for argument's sake, I'm just going to show you the hydrogen peroxide and the water. If you notice, the rate of hydrogen peroxide being lost is going to be the same as water being produced. So water might look like this. It's being produced. Times 0. Okay, well, the hydrogen peroxide is going to be the mirror image of that. It's going to be the same slope but going in the exact opposite direction. And we can do the same thing we did before, the initial rate, the instantaneous rate, or something like that. And I'm going to use some actual data here to show you an example. Okay. Well, let me show you some data. I'm not sure I have another slide here, so I may just do some erasing. And yeah, I think that'll work. So I'm kind of skimming through my notes here and trying to streamline them a little bit, so I'm not taking up too much time. Fine. So let me see if I can make a table here. And I actually just stole this from your book. So I'm actually taking this from section 12.1. So you're given some data here. And let me give you some sample data. And this reaction is not very fast, so we're measuring time here in hours. And we're going for 12 hours. So we're going to look at 0 hours, 6 hours, and 12 hours. And remember, we talked about the average rate before. We actually have to do a little bit of math. So what do we need here? So 6, and we'll use molarity. And when this reaction starts, we're using nice, easy numbers. So we make up a solution of hydrogen peroxide that we think has an initial molarity of 1. After 6 hours, it gets cut in half. After 12 hours, it gets cut in half again. Fine. And I'm going to need some space, so I'm going to erase the graphs. Maybe that's not so good, but it'd be nice for you to have those available. I just don't know if I have another blank slide, and when I don't have enough of those, it gets confusing. As I erase this, one thing we do, we always report rates. I'm going to rewrite this up here. This is taken exactly from section. So if what I'm saying here is confusing or I go too fast, I'm not doing a very good job. Oh no. Oh, okay. I'm going to have to use this slide. So ignore this. Pardon me. Made a mistake. So ignore that for now. I'll erase this stuff. If you want to calculate a rate, so what we're going to do is subtract the two successive concentrations. So we're going to take, and you can do this on your own. So we're going to take concentration 2 minus concentration 1 divided by time 2 minus time 1. Well, let's just do an example. So if we want to do the first time interval, we would take, let's see, the concentration at time 2, which is 6 hours, 0.500 molar, minus 1.00 molar. Well, that's pretty easy. That's going to be negative. And since this is a decomposition, we're going to put that negative sign here. This will make more sense. We always report rates as positive, even though this math is going to give us a negative answer. And the time 2 is 6.00 hours minus 0.00 hours. So that would be the average rate over the first time interval. And you can do that for the second time interval. So you'll take 0.250 minus 0.50 and then 12 hours minus 6 hours. So I'm not going to do that one here for you. But if you do that, you can double check my math. I think you get a number that's 0.0833. And what are the units there? Well, that's going to be molarity per hour. Another way of writing that is moles over liters, because that's molarity, times hour. I'm not too worried about that right now. So ultimately, what you get is a table that looks like this. This is what I wanted to finish on the other slide, but I messed up. So I'm going to have to rewrite this, sorry. So time in hours, 0.00, 6.00, 12.00, concentration, 1.00, 0.500, and 0.250. So the concentration goes down by half successively. And you end up getting the following rates. And the units on this are moles over liters times hours. Well, the first rate is irrelevant because we're not going backwards in time. There is no rate there. What I want you to see is here's the first rate, 0.0833. And then what happens to the second rate? You can probably guess. The rate gets cut in half. So the rate is not constant. So the time doubled and the rate got cut in half. The concentration got cut in half. That's a direct proportion. That doesn't always happen that way. And these are average rates. That's all I want to kind of show you here is the basics of chemical kinetics. Now I'm going to erase all this stuff and we want to take some notes. So it's going to take me a second here to erase all this because not the most professional video, but by now you're probably used to that. And then we'll do some sample problems in class because I don't think I'm going to do any more problems with this. And the notes are basically just what I mentioned to you. All the things I was talking about while doing these two case studies. So let's go ahead and just let me put them on the slide for you here. There we go. I'm not really sure I have much to say here. This is just a set of notes for the that I did. Okay, so chemical kinetics is a reaction rate, so it's time-dependent change based on amount. And there's lots of things we can use to measure amount. We can measure moles, we can measure molarity, we can measure pressure. In some cases, we can measure volume. You might remember the graphs that we did before with absorbance and wavelength. Well, we can measure the absorbance of some chemical if it changes over time, if it goes away, like chlorophyll decomposes or something, we can do that. And these are all the things we mentioned before. The average rate is over a specific time interval. The instantaneous rate is at a specific time, that's that tangent line, and the initial rate is at time equals 0. We will use those somewhat interchangeably as proxies for rate. And then finally, rates are relative. These are called relative reaction rates. Fine. I'm going to move ahead here just to see what we have, but I have a feeling we're going to do more examples in class because the video is almost half an hour long already. Let me just see what we have here coming up. Yep. You can try these on your own, but we're going to do these in class. So I give you a rate based on hydrogen peroxide decomposition. Fine. You're just told that information, the tangent of the line. What would the rates of water and oxygen be through the coefficients? Fine, you can do that. Try it on your own if you like. We'll do that in class. Yeah, same kind of problem. You're given a rate of production of ammonia. What would the associate rates of consumption of hydrogen and nitrogen be? Again, try them on your own. Get a number. Let's not do this in the abstract, but we'll do that in class. I think that'll be just fine. And we're going to leave here. Hydrogen peroxide. Oh, I gave it away. It's always fun just to do things. What are these things? No? Okay. Well, what's on the left are obviously tomatoes. And does anybody know what's on the right? Well, those are those are white blood cells. And your body, one of the things it does with its immune system, so these are, I just did this for interest's sake because hydrogen peroxide is really important in nature. Hydrogen peroxide is actually a defense mechanism. It can actually be used to pop the cell walls of invading cells, like invading bacteria and things like this. Plants do this. Humans do this. Your white blood cells, what they essentially do is surround an invading molecule, or well, not molecule, an invading cell, hold onto it, and essentially spray it with hydrogen peroxide until the cell walls pop. That's called apoptosis. Just an example. Okay, that is an introduction to chemical kinetics. So your basic definitions, what do you want to take away from that? Well, how do you take kinetic data? How do you calculate a rate? For now, we're just doing average rates over a time interval, given the information, and we'll go from there. Excellent work, and we'll see you next go around.